So the BT guys, well, at least Steve and Kev kept me up till 4:30 in the morning drinking. So I'm a little bit tired. So I'll be Red Bulling. Yeah. Right. So I'm Graham Sutherland. If you follow me on Twitter, you might know me for party hats, gas masks, and exorbitantly expensive microscopes. Yes. So I'm a penetration tester by trade, and I work for Cisco by way of portcullis. We got bought. So this talk, I'm going to go into a bit of background as to what I was doing, some sort of discussion of how I went about reverse engineering this wonderful little computer, some approaches to building a mod for it, the way I went about the design, the fabrication, and what results I got, and what I would like to do in future. So the background. This is the subject. So this is the first thing I wrote a line of code on, ever. It's a kid's toy, made by VTech. This is the same line of toys. This is how they marketed it in the US. In the UK, they told you all about the, the educational benefits and the quality of the toy. And in the US, they made this ad. That is not me.
Are video games having a dramatic effect on your child? Get Video Smarts and change all that with the most complete library of tapes, starring Teach and Teddy.
Hi, boys and girls. Let's find the space with the letter C.
And Professor Set.
2 plus 1 equals...
Good girl.
And Mr. Mayor.
Listen to my vowel friends.
A-E-I-U.
Get Video Smarts and turn your video monster
into a child with video smarts.
Only slightly patronizing. But yes, super scary video games. So a little bit of history. 1988, I was born. And more importantly, VTech released the pre-computer range. And in 1994, my parents bought me this VTech pre-computer 1000. And as all kids do, I hammered all the buttons to see what happens. And I got it stuck in computer drill mode. And apparently computer drill means basic. It turns out it has a basic interpreter on it, and I read the manual and I learned basic when I was 6. That was fun. Yeah, 1995 to 2013, education and stuff. I taught myself some programming, and I taught myself some electronics. My dad helped out a fair bit because he's an electronics engineer, which was quite nice. But sometime during that time, my pre-computer 1000 was sold. To be honest, I'd forgotten about it at that point. 2013, got my first pen testing job at Portcullis. Start getting into the demo scene. I'll explain a little bit about what that is in a moment. But 2015, so back in December, we got acquired by Cisco. So I guess I work for them now. Back in May, I had a random thought. I went, you remember that old thing? That was kind of cool. I could write a demo on that. So I got one on eBay for 20 quid, which was awesome. And all the nostalgia. And then remembered it had absolutely no save function. You write a program in that, you turn it off, and it loses everything. It has no EEPROM or nothing to save code onto. So yeah, kind of hard to write a demo without storage. So between June and August, I learned about Z80 system architecture, started designing a save mod for it so I could actually save my basic programs. So I went through a few design iterations, finalized the board up, got them made, life stuff happened as it does, and then it came up to September 2016, and I went, oh shit, I forgot it's 44con soon, and I'm meant to be doing a talk on this. So, as you do. So I ordered all the parts, soldered it all together, and then end result, and I will talk to you about that in a bit. And then today is my 44con talk. Woo. So, as a side note, the demo scene is something I got into a little bit back, and this is why I decided I wanted to sort of mess with this little bit of old hardware. So, demoscene is basically about pushing hardware as hard as it will go. So there's a lot of people still messing with like old retro stuff, ZX Spectrum, C64, Amiga, but it's also like modern computers as well, so like pushing them as hard as they will go. This is a demo by CNCD and Fairlight. It's one of the coolest things I've ever seen done on a computer with graphics and music. But yeah, it's basically all about like old school graphics, music, and also new school stuff, and just generally being creative with computers. So I thought if I could do like a little demo on an old VTech where most of the creativity was actually just the hardware mod, because all it's got is a one-line LCD text-based display. You can't put any graphics on that, but you can make little bits of music on it. But yeah, so I thought that would be quite fun. So obviously, what's the first thing you do when you get a cool piece of hardware? You take it apart, see how it works. So the general process was I took it apart, and I started to look at all the individual parts on the board, what ICs are on there, so what chips are on there, then looking at like common circuitry. So if you see certain types of parts next to each other, you can sort of assume what their function is based on the way they're all sort of laid out. Then do some stuff with photographic overlays, so taking photos of each side of the board and then overlaying them so that you can map traces around and see what's connected to what. And if you follow the traces, you get a circuit. So the tools, a camera, Google, bit of logical thinking, multimeter and an oscilloscope. It's stuff you can pretty much, there's not a lot of cost there. The camera can be your phone camera. You don't need anything crazy macro lenses or anything like that. I did all of this with just the camera on my phone. And the oscilloscope isn't even technically necessary, but it's useful. And also microscopes are useful, as I found out the other day when I bought a ridiculously expensive one. So this is the board. Old school. So yeah, yeah, no surface mount, all through hole. This is all 5-volt logic. No, double side. It's mostly single-sided tracers. The other side, they just literally went, oh no, we're going to put a big load of bridges on it. So yeah, that's kind of cool. Yeah, all these big, beefy chips. Yeah, no connectors internally onto the board. It's all directly soldered in. So all of those ribbons and everything are just directly soldered straight into the board. It's proper old school. When I show you the overlay with the tracers in a bit, you'll see how cool that side of it is. I didn't actually put a single photo of the back of the board on here. I should have. So start through identifying the chips. If you've got bad vision, then microscopes and zoom lenses work wonders so that you can see. So this is a Zilog Z80C0006PFC, something like that. So I look at that and go, probably a Z80, because I know Zilog makes Z80s and Z84 is usually a Z80. IC number 2, this is a Sharp LH5116. So Google that one. VTech, if you can see just behind that label, it's got a VTech video technology chip. It's an LH531606, and then I thought, well, I have no idea what that is either. I'm guessing if it says VTech on it, it's something custom, and I'm guessing that it's probably the ROM. But, then this HEF 4508 BP. Again, I couldn't remember off the top of my head what that is. Somebody probably can. But, So, started digging through. So we've got a Zilog Z84, which is a Z CPU. Sharp LH5516, from where it was on the board, kind of next to the processor. So I thought, RAM. The so-called VTech chip, probably a Sharp as well, because it's got that same LH prefix, the LH5. So it's probably a Sharp chip as well. It's just been rebranded. And an unknown brand, HEF 4508 BP. Let's find out what they are. So you just Google them, and you find the data sheets. So we know it's a Zilog Z80 on the top. The Sharp LH5116 is 16 kbit of static RAM, so it's SRAM. when I Googled that LH531606, they got no hits, but if you take off the 06, it turns out there's a mask ROM from Sharp, so it looks like it is exactly that. The part number that I got the datasheet for is not exactly right. It's got like the wrong pin count and stuff, but you can sort of assume that it's similar functionality because it's generally they don't make serial numbers match like that for no reason. And then the bottom one is a dual 4-bit latch, which I know just from looking at it is not going to be massively interesting from what we actually want to do, because what you're really interested in is the processor itself, the RAM, and the ROM. Now, mask ROM is basically you write to it once, and you can read back as many times as you like, but that's it. There's no rewriting. In fact, it's usually like factory burned in, hence why it's a custom chip with the VTech logo on it. So common circuitry. Now, this at the top, this little selection here. Does anybody know what 7404 IC is? Somebody knows? Yeah, inverter. So it's a hex inverter. And if you see a hex inverter, well, you see a bunch of inverters together with a bunch of capacitors and resistors, you can make some assumptions as to what that might do. It's a ring oscillator. Now, ring oscillators are kind of cool. Essentially, it's a ring of inverters that sit in an unstable state. So an inverter, you take a low voltage on the input, and it'll put a high voltage on the output. So a 0 on the input, you get a 1 out the output. And if your input is a 0, then the output of the first inverter is a 1, which means the output of the second inverter is a 0, which means the output of the third inverter is a 1. But that means that the input is now a 1. It was a 0 originally. So then it flips. And it flips backwards and forwards and backwards and forwards and backwards and forwards. Now you might think that just goes into some sort of weird state because if it's, you know, the logic doesn't pan out, it doesn't work. But there's what's called propagation delay. Now, let's say each of those gates takes 5 nanoseconds to switch, so it goes between off and on. The formula for the frequency of a ring oscillator is 2 times the number of gates multiplied by the time it takes for each of those gates to change. So if you work that out, that ring oscillator would be 33 megahertz. And that's if you just use the inverters all directly connected together. Now, that's not super accurate because, you know, just due to variances in manufacture, it can go different ways. Now, in our oscillator, again, we can sort of assume it's a ring oscillator by looking at it, and I did verify this by following the traces. But by adding the resistors and capacitors in there, you can essentially increase the amount of time it takes for a transition to register. So you can essentially produce a much slower oscillator, or you can control the frequency of that oscillator. And in this case, it's 2 megahertz. So that provides the clock signal to the entire system. And it's a super simple design, which you might expect out of a toy like that. So extracting a diagram from it. So take a photo of the top, take a photo of the bottom, normalize it, so let's skew it so it's nice and flat and sits kind of square. Overlay the two. So I'd like to do that in like Photoshop or Paint.net or GIMP or whatever, so that you can change the transparency of each side and look at different sides a little bit more. And then you can add multiple layers so that when you're drawing traces over the top of it, you can switch between which sections of the traces you want to view at any time. So it's quite nice to go through that. So you enumerate all the pins on the board and then trace a map between them. And you get something that looks like that. And I do love how all these traces are super curvy. You never see that on modern boards anymore, but it looks super cool. I don't know how well you can see that, but it's a shame I didn't put. Yeah, it's a shame I didn't put a picture of the bottom just as is on it. But yeah. Did I not? Oh, here we go. Yeah. So yeah, the general methodology for mapping them out is you take a known pin, so you can look up the data sheet for a part, or you can go, right, well, I know that this bit coming out of this bit of circuitry is probably this because I've measured it. Map that to all the locations so you know where it's being fed. Use that information to identify other pins, trace those, confirm with measurements, and just repeat and repeat and repeat until you've got a circuit diagram out of it and you know what's connected to where. So here's my horrible MS Paint style doing it freehand, but literally you've got the 7404 inverter on the bottom, which is creating that clock signal, which goes across to the clock input pin on the Z80, which then comes across and connects over a little wire bridge, which goes all the way up to that top left-hand corner, which is the, it's got like an expansion port. So it's basically pumping the clock signal out the expansion port. Now, as a side note, this is something that Mika Scott posted on Twitter the other day, and she has done this with a more modern board, and that looks a lot more pretty than what I did. And it's a lot cleaner and easier to read. So if you're going to do it, that's the right way to do it. Mine was just the half-assed method of doing it. So the approach is to sort of coming up with a save functionality mod. There's two main ways that I considered doing. One is completely replace the ROM. So basically, get a microcontroller and make that pretend to be the ROM. Modify the code so that when a certain sequence of, like maybe add a new command into the basic interpreter that saves and loads, or essentially just monitor for a certain set of keys being pressed at the same time or whatever, and then it will save that back into the ROM somehow. Alternative way was to man in the middle of the RAM. There's two approaches to that. One, you could just passively man in the middle of the RAM. However, downside of that is saving, you can't be passive, sorry, loading it back into the memory, you can't really be passive with that. And also you've got to rely on the processor actually doing the memory fetches and you being able to catch them. The other way of doing it is to completely disconnect the RAM from the processor temporarily, have your microcontroller then dump the RAM, save it somewhere, and then give the RAM back to the processor. So yeah, so the ROM, fairly simple circuitry, but I'd need to learn Z80 assembly, and I don't know Z80 assembly. I'd also need to discover how that ROM IC works, because as I said, there's no data sheet, and it seems to be a custom part. It's possible to learn how it works, but that's kind of a pain. But it is potentially more seamless, and you could literally just have a command that would do it. Man in the middle in the RAM, it's more complicated circuitry. However, you don't need to learn Z80 assembly. The RAM IC is a known part already. The Z80 is synchronous, which means that you can basically take the clock signal and just stop it, and the Z80 will just halt in its state pretty much as long as you've got power connected to it. Whereas with a lot of more modern devices, they're not synchronous, so if you stop them, what happens is they expect internal memory registers and things like that, internal registered memory, to be refreshed every so often. And if the clock isn't running, then what happens is it just loses all internal state and stops working. Same happens for like DDR RAM. You need to refresh it repeatedly. The Z80 also has shared memory bus support, which is kind of cool. So you can actually say to the Z80, hi, I'd like to take over the memory bus, and then you wait for it to say, okay, I'm not accessing the memory bus right now, and then you can do whatever you like with it. So it's kind of like really early DMA, almost. Like really early. Okay, so the design. So now I know sort of what I want to do. Oh yeah, I should probably say I decided for the second approach because I'm lazy and don't want to learn Z80 assembly, although I will at some point. So the main challenges, in terms of design, I want to keep it simple. And in terms of debugging, I wanted to be able to debug it reasonably easily. The other challenge is part selection. So obviously cost is a factor. Also complexity. So if you're buying particular parts, you might be able to get some cheap ones, but they require a lot of additional like supporting components, and that can also drive your cost up, but it can also drive up the complexity and build time and things like that, and different elements that you have to debug. Size. I don't want a board this big connected to a little computer. Also, bigger your board manufacturing costs. You send them over to China, you get little boards, cost you $10 to get them made. Make them twice the size, cost you $30. So there's a big difference in terms of price as you start scaling up the board size. Voltage. A lot of modern components only run at 3.3 volts, particularly all the CMOS stuff. whereas this is old vintage, practically TTL hardware running on 5 volts. So finding parts that were both reasonably cheap, not too complicated, not too big, and available for 5-volt logic, and fast enough to do all of the, basically handle a 2 megahertz, a device operating at 2 megahertz. And also board design. Again, size, electromagnetic interference, so ensuring that high-speed tracers are actually routed in a way that isn't going to cause them to interfere with each other because they're next to each other. Decoupling, which is essentially if you've got a device that's varying its amount of power quite a lot, what can happen is the impedance of the tracers, which is like AC resistance of the tracers, causes a delay in power being delivered to the device. And if you don't put in what's called decoupling capacitors, which act as like small local energy reservoirs, what can happen is your device will start glitching out for all sorts of reasons, and you'll spend ages debugging it, and it turns out it's just a power issue. It can also cause more EMI if you don't do it right. And the mechanical aspects of it as well, because if you're going to design something that's going to attach to the board, you want it to attach to the board in a reasonably easy way to deal with. You don't want it to be, sticking a bunch of wires outside of the board and then connecting it up, and then, it just looks like a total mess. You would like it to be in situ, so just designing it so that it can sort of fit in with the existing system. So a rough idea. So there's a particular type of IC called multiplexer demultiplexer, or a muxer demuxer. Think of this like a two-way switch. So let's say you've got a memory address line. Well, that's a bad example. Let's say you've got a data line, a data bus. So you've got, let's say it's an 8-bit data bus. So you've got 8 lines, bit 0 through bit 7. When you're writing data to the memory, the device, the processor, is sending data to down that data bus. When it's reading it, it's taking that data back out of that data bus. It's a bidirectional line. It can be driven through either side. Now, what a muxer demuxer can do is it's like a digital switch. So you say, I would like you to flip the switch this way, which means that the RAM gets connected to the processor. I would like you to flip the switch the other way, which means that now the RAM is connected to an external microcontroller or whatever. They are literally just like digital switches. And usually what happens is you'll get one chip, and it will have like 3 or 4 muxer demuxer switches in there, and you'll have a single pin, which you say, set the pin to low voltage, and it will flip all of the switches one way, set it to high voltage, and it will switch all of them the other way. Dead simple. You can drive that off a microcontroller, super simple. So an Atmel microcontroller for driving that and interfacing with the rest of the Z80. Cutting off that clock, so that clock that was being provided by the provided on board, 2 megahertz is kind of fast. Slowing down the clock isn't really a big deal. 2 megahertz is kind of fast for doing a lot of monitoring of the I/O lines and stuff. So the idea is, usually it runs full speed. I go to press the button to say, oh, I would like to save, and it just drops the clock frequency right down so we can handle things a little bit more at our pace, and it also makes it easier to debug. And then finally, monitoring the Z80 I/O control lines, or using wait and bus request and bus ACK. So the Z80 has these three pins. I'll get this right. So what wait does is if you set the wait pin on a Z80, the processor will essentially try to halt. You can also use bus request and bus ACK, which is like that the shared memory bus system that it uses. So you basically set the bus request pin on the Z80, so you basically just connect that one to, I think you just connect it to ground, and it will then set the bus ACK pin high or low, I don't remember which way it is, to say, yeah, cool, you can take over the RAM, or the memory bus rather, and then you can let go of the bus request pin, and then the Z80 will just carry on. And that's just built in. So it's like a nice little sort of half-assed DMA system. So the goals for the board. Try and get the muxer demuxer ICs under the RAM. Now you saw that RAM chip. It's not very big. It's like, what, that big? And I needed to get 6 ICs under that. It's a bit of a challenge. And also I wanted the boards to be 50 by 50 millimeters at most, because that's where the sweet point is for pricing on getting boards made in China. Because you can get boards like that made for $10, like 10 of them for $10. 2-layer board, so just one side and the other. Standard thickness, standard copper weight, all the usual stuff. 8mm traces. Most people, most places say try to use 8mm traces or larger. 8mm just is the width of the trace. Some of them end up using 6mm. Most board manufacturers will allow you to do that, so it's fine. Once you go below a certain amount, the tolerances get really sketchy, and some of the traces might not be quite right, and you can have defective boards. I tried to route the same signals together, so when you've got, say, one address line coming off the memory, and then you're switching it between the Z80 and the microcontroller, I'm trying to route all 3 of those lines together so that if there is any interference between those lines, it doesn't really matter that much because they're all carrying literally the same data. Using ground pores. Ground pores are essentially connecting all of the empty space on the board to ground. So you basically leave all the copper on the board where you can, etch out where you're going to have other traces going through that, and then just pour copper all over the rest of it, and then connect that to ground. And what that does is, one, provides you really easy access to just be able to stick a decoupling cap off something straight onto the ground, but also it's good for electromagnetic interference, because if you're running a high-frequency line through a ground pore, it tends to not emit quite as much energy. I don't understand that quite so much because physics. But I just know that that's a general rule. And power and switch indicators. I wanted to have one LED that says I'm actually getting power, and another one that shows the state of whether I'm switched between the microcontroller and the Z80 having access to the RAM. So this is an early design. So that's the RAM chip, and these are the muxer demuxer ICs sitting underneath it. So I started routing these. Then this is my second design, which was going a bit better. You can see I managed to route everything underneath. And this is the finalized second design. So this is the one that I almost sent to production. So the idea is there, you've got the selection pins here. So these pins here, if you tie those together, that will switch across. And then if you set this pin to high voltage, I think it's that one. Yeah, that one. To high voltage, it switches the other way. So that's literally what's switching between them. And then the idea is that these inner pins connect to a header on the underside, which then plugs back into where the RAM was originally on the board. The RAM sits in this block here, where it says LH5116 SRAM. So the inner headers there connect back into the original board, and the outer headers connect out to the microcontroller so that it can then take over when it needs to. Bits on the bottom is just decoupling caps and the LEDs on the left, and just a couple of transistors. Then it turns out that the original ICs that I wanted to use, which are in what's called an SSOP package, it turns out they weren't made anymore. So Farnell listed them as in stock. By the time I went to go back a couple of months later and actually go buy the parts, they were no longer in stock and no longer manufactured. That was annoying. Oh, yeah, you know, just buy the dodgy ones off wherever and keep your fingers crossed. So yeah, that was a pain. So it turns out that they'd replaced the entire line with what's called NSOIC, which is a narrow, small outline IC, thank you. So they're slightly thinner. They're basically the same pitch, in terms of, so the distance between the pins is the same, but they're thinner, which was actually quite good because it means I had a little bit more space between things and I could route things in a little bit nicer way. But it did take me like 2 days to do the rerouting on everything. That was a pain. So this is version 3. So this is the top. Looks kind of weird with the ground pores in, doesn't it? But essentially you can see as like where all these traces are cutting through the ground pores. And then this is the bottom. So this is where all of the surface mount muxer demuxer chips were soldered in. And then obviously you've got the headers and whatever. Most of the stuff is actually on the bottom side. It's kind of weirdly drawn. So yeah, did that. Onto fabrication. So I use Electro. There are so many manufacturers for PCBs out there that everybody's got their own preferred one. I like Electro because they're cheap. They're not the fastest people in the world. It takes a while. 4 to 7 day lead time on manufacture, unless you bump it up to do rush jobs like that. At $9.90 for 10 boards, I really can't complain. However, once you add in a 24-hour rush job, which I had to do because I forgot to order the boards till too late, I ended up paying $25 on that, and then you have to pay for shipping. And shipping, by default, like I think about $16 shipping, takes about a month to arrive. If you want next day, get your wallet out. Because just shipping those boards from China alone, I think to get 10 boards made in total, it cost me just over $90 because next day shipping from China. Because you have to get it on like DHL, super delivery or whatever. I'm pretty sure they lie about what it costs. But anyway, if you don't really care about how long it takes for them to arrive, then you can do it super cheap. In fact, how many of you are familiar with White Hat Rally? Hands up. Oh, wow, not that many of you. Okay. All right. Okay. White Hat Rally is like a charity event where basically people go drive around in a car of a dressed and, well, they dress themselves and the car in a particular theme. It's usually for Bernardo's, I believe. And sorry, is it Childline now? Okay, right. But yeah, basically, and then security companies and other companies, I suppose, enter teams and go and drive around a particular route and complete challenges and all sorts of fun things. So when Portcullis did that for 1 year, they went as the Ghostbusters. So we got a bunch of vacuum cleaners, and I built some little flashing light kits, and I used Electro for building the boards for that. And that was kind of fun. So that was the first time I'd ever used them. So yeah, they're fine. Parts, I use Farnell. I have no reason to use anybody else because they've got such a stupidly large part selection. The search system is absolutely epic. Like the filters on it is just like, oh, I would like to have this specification between these 2 levels, and it will just go like, filter it down, filter it down, filter it down. Yeah, it's just so good. And it's got data sheets directly in there. They've got like automatic, you can do like the whole chat to somebody online thing. It's great. And decent prices as well. And I think is it next day shipping now for free, which is kind of awesome. Yeah, so if there's, well, the shipping is technically free, but orders under £20 carry a £3.50 administration charge, which is like bollocks. It is before that is true. But to be honest, yeah. Oh yeah, they changed the bloody policy. But last time I tried, it was free shipping, so yeah. I do like them though. And also they do the whole Element 14 thing, so all the Raspberry Pi reselling Arduino stuff. So the assembly of the boards, I did it all manually. It was, yes, 60-40 tin lead solder because ROHS can suck it. I hate lead-free solder. It's awful. It flows like a beast. I mean, you know, it might kill you, but I'm not dead yet. So, fun little side story. When I was a kid, far before I can remember, in fact, I think it was about the time. You remember those little bouncy things that you used to stick to doorways, like little kiddie bouncers? I must have been like 2 or something, in one of them. And my mum used to work for 3M, and she soldered kettles together. So she used to sit there with a soldering iron, soldering kettles together while I was bouncing in that. So I think that I've probably breathed in plenty of lead over my lifetime. It explains a lot, really, doesn't it? So anyway, manually solder it. Flux is awesome. If you just solder with normal solder, yeah, sure, that's fine. Add a bunch of flux to that, and suddenly everything's flowing wonderfully. Everything's moving into place. It's just so cool. Just buy pots of it. It's awesome. It is awesome. Just make sure you don't get the stuff that plumbers use. Plumbing flux is not the same. It's acid-based, and it will just eat your boards. Yeah, rosin is the good stuff. So anyway, get a decent soldering iron. You don't need these epic, stupid priced ones. Mine was reasonably priced. They are good. Oh yeah. Yeah, so I've got, yeah, exactly. I mean, I spent like, what, 200 odd quid on mine, maybe a little bit more. It's a Hakko FX888D, which is £200 technically less than the car. It's about 100 quid less than the car. Hey, the car still works. Anyway, nice little small bevel tip. Some people like pencil tips, some people like chisel tips. I like bevel tips, they're easy to use. Do your small parts first, because you don't want big things standing off the board, because you turn it upside down and your board's all sat wonky and it's a pain in the arse. So do your small surface mount stuff first. That's one. Flux acts like an adhesive almost. It will just stick things in place. So when you're placing your parts, if you've got a bit of flux down, you pop the part on and it doesn't just immediately like flick across the board as soon as you accidentally nudge it or whatever. It tends to sit in place. Yeah, narrow SOIC is an absolute pain in the arse. It's tiny and fiddly and yeah. Yeah, I'm gonna. I mean, it might just be that I'm terrible. It's probably that I'm terrible. Fixing bridges with solder wick. Solder wick is cool. So solder wick is like, well, it's also known as solder braid. It looks like braid, but it's like copper, and it's kind of like absorbent for solder, but it's thermally conductive. It's made out of metal, and you basically, there you go. Yeah. So when you've got a bridge between 2 pins, so you're soldering in SOIC or any surface mount part with lots of little pins next to each other, and you get a bridge over it, and then you're running your soldering iron over it, and you can't flick the solder off, and it gets really irritating. This stuff, stick it across, run the soldering iron off, pull it off, and it goes, oh, there's all the excess solder gone. It's bloody fantastic. And the microscope is a lifesaver. Yeah, it's so awesome. I spent more on the microscope than on my car. It's also really heavy. Like the guys, so if you follow me on Twitter, you may have seen this bit already. But so I ordered this crazy microscope, to which I was like, when I was debating buying it, I turned to my wife and I said, "Oh, I don't know whether I should buy it. You know, it would be really cool." And she just went, "You know you're gonna buy it, so why are you even asking me?" Anyway, DHL turns up, and the guy's pulling this massive box on a pump truck. And I'm looking at him like, what have you put in that box? And are you an absolute pansy? There's a microscope in that. And then this guy's not small, so he lifts it onto my front doorstep, and he looks like he's struggling a bit. I'm thinking, what on earth has he got in here? So I sign for it, close the door, go to pick it up, and I couldn't budge it a bloody inch. The stand is made of about 2-inch thick steel. It's got steel bar everywhere. It's got a big counterweight. It weighs an absolute ton. The microscope itself, you could juggle the damn thing, but the stand is a bloody ton. Both arms and a leg carrying it upstairs. But it's awesome. So, I did not buy 2. That would probably not go down well. It's in a bedroom. So anyway, yeah, so the microscope is great because you can basically look directly down at the pins and see which ones are soldered and which ones aren't soldered. You can see tiny little bridges of solder that you wouldn't have otherwise been able to see. They're great for surface mount stuff. You don't need to spend 450 quid on one. Oh, yeah, yeah. Yep, pretty much. The result. So this is what it looks like from the top. And that's what it looks like from the bottom. It's not too bad. And that's what it looks like with the RAM chip in it. So I desoldered that RAM chip using the desoldering braid. So this, the original solder that was on there was leaded because ye olde soldering. But the thing is, because it's been sat there for so long, it's kind of a pain to get your iron to heat it. So pro tip, put a little bit of solder already on your iron, tap each of the pins so it remelts the solder, then run through with the solder braid. And again, flux because it's awesome. So I got that chip off with all of the pins dead straight. No tugging or anything, literally just took all the solder off. It was great. So this board, what I've essentially done is stick an IC socket back where the original memory chip was, and then this riser board at the bottom plugs into it. The riser board goes out, connects to those inner headers, which are just underneath, and then everything sits on top. So that's what my surface mount soldering looks like up close. I took that with my phone camera through the microscope. Sorry? Yeah. Solder suckers are still a thing. I hate them and they're terrible. I don't know anybody who can still use them and say, do you like them? I don't like them. They're terrible. The vacuum ones. Yeah, yeah. So they're great. Yeah. The only problem with those is that they're, again, more expensive than my car. Oh, okay, yeah, okay, right, second-hand on eBay. Yeah, they suck at sucking. Let's not go there. So yeah, so this was taken through the microscope with my phone's camera. You would not believe how hard it is to hold your phone that steady to take that photo. It took about 6 attempts to get that. So that's the board in situ. The all-important question, does it work? Put your hand up if you think it worked. No! Don't bloody work, does it? So, why does it not work? I have a few theories. To be honest, I ran out of time to work out why it doesn't work. I have theories. So, theory number one is that it turns out that the ENSOIC model, the transition time on the internal gates switching on and off in the muxer demuxers is about 3 times as long. It doesn't actually tell you this in the datasheet. It tells you this in the errata from the notification that they discontinued the old one and replaced it with the ENSOIC. Yes, so when they switched the packages over, something that they did, I don't know whether it's like the new, they changed like the die process or something, and it actually takes slightly longer to switch over. I don't know why it is. Yeah, exactly, 3 times as more. I mean, we're still talking in the sort of like tens, hundreds of nanoseconds sort of time, but yeah, it's kind of stupid. Maybe I overheated the muxer demuxer ICs when I was soldering them and killed them. I've got some spares. I'm going to redo another board and see if it works. But yeah, I had a bit of a look around, and they do some kind of weird things. Some of them don't seem to go like up to full voltage and stuff. There is a note in the data sheet that says that if any of the, so if I just go back slightly, so you see, I don't think you can see, there's probably a bad photo for that. Better photo, better photo. Okay, so you see those headers at the top? So there are two muxa-demuxa switch parts in the last IC that aren't used. And there's a note in the data sheet that essentially says if you don't connect them, it can do weird things and have problems because you're leaving them floating. And it may also be that there's some intricacies with the RAM chip that does leave some of them floating sometimes. It says that it can cause some problems. I'm kind of not convinced on that because if you're just leaving them floating, surely that's not going to cause any problems at all. It shouldn't. That's the whole point of a muxa-demuxa. You should be able to do that with them. So, or it could be something else. I ran out of time. So, disappointing. But I will bloody get it working. So this is the current state of it. This was yesterday. This is my little lab. So that's my crazy microscope. Yeah, so this was me trying to fervently trying to get it working at like 3 in the morning. In fact, no, it wasn't 3 in the morning. It was about 10 minutes before my taxi was due to arrive to take me to the train station so I could come here. Yeah. Okay, so future. What did I learn? Don't blindly trust the data sheets. Dig around, find all of the supporting documents, and find, especially when there's a part change, just don't trust what was in the original data sheet. Yeah, measure things twice, thrice, and whatever the fourth version of that is, which I guess might be thrice, I don't know. Yeah, a lot. Yes, measure things, basically check continuity across things when you're soldering, because maybe I don't know, screwed something up and powered it and it blew something up. I don't know. I don't think I did, but yeah, triple or quadruple your estimated time. This took way longer than I thought it was going to. Board respins take time, and rush jobs are so expensive. We're talking $10 to $90 just to get some boards redone. It's just super, super expensive. Debugging is really important as well. At the moment, it's a real pain in the arse to actually debug this board because I have to clip onto the individual pins, and most of the stuff I've got to do that is an absolute ball ache. And factor time into cost savings. So in general, spend more money, spend less time. Hello. Yeah, also that. So Tim says expense it. I feel like that's, you know, management approval. He did say Cisco. Excellent. That's the business expense. The big problem with breadboard is that when you're doing it at 2 megahertz, it's just not appropriate. Like, it will just throw all sorts of horrible EMI. Like the impedance of the traces will be awful. It just won't work. Yeah, it's also that. It just takes longer to get the circuit boards made, but the fact that you've got to trace everything round on the it's such a ball ache. Yeah, it's probably about the equivalent of $10 already.
So you can actually get 5 circuit boards made and delivered to China in the same time as your own design.
Yeah.
Cut any track.
Yeah.
Run any.
Yeah. Yeah, variable is fine for really simple designs, but otherwise, yeah, just go for PCBs. Yeah, exactly. It's nice to have a little bit lying around, because if you want to prototype something, you go, oh, yeah, I'll just go and job done. Yeah. So what I would do differently is make debugging easier. At the moment, it's a pain, so I would add more debugging headers, probably like a dedicated test rig so that I can literally just plug a cable in and then have it break out to all of the things that I want to check. Test points on the board, I didn't put any on the board. That was dumb. Need to do that next time. Review the parts better. Understand what they're doing, and especially when they make a change. Definitely increase the time estimates. It takes so much time. You spend ages doing things, and then you change your mind about how you want to do something. It's getting too complicated, so you switch around, do it in a different way. It just takes forever, especially when you've not got a huge amount of experience doing this kind of thing, because this is the first board of anywhere near this complexity that I've ever built. Yeah, spend more money and work less, because, like, to be honest, the amount it's actually really costing to make it, spend a bit more, have it simpler, and just be more convenient, because otherwise you just get frustrated with it taking forever and you don't really finish things quickly. So yeah, if you want to follow me on Twitter, I will definitely be continuing to tweet about this with my debugging process and getting it working. Maybe next time I'll come back next year and go, look, I built it. In fact, you know what? I'm tempted to submit to next year's CFP and then just not tell you whether it's working yet. Okay, cool. Did not know that. Right, any questions?